A user report of a slow page instantly opens up a massive diagnostic search space for the developer. A single web request is actually a stack of isolated systems. The latency could live in the database, the PHP application logic, the framework bootstrap, or the browser's own rendering thread. Guessing which of these layers is failing leads to engineering hours spent optimizing code that was never the problem. Modern pages are far too dense for manual tracing. A single load is built from dozens of database calls, templates, and render blocks. Resolving this latency requires moving from a vague symptom to pinpointing the exact layer of failure before touching a single line of code. A common professional misconception suggests that if a web application tests fast on a local development machine, it will perform identically in a production environment. Pristine local environments mask critical variables. They emit real-world network latency, heavy concurrent traffic, or sudden caching failures. To find the truth, we need telemetry from live, authenticated production sessions. This is the diagnostic pipeline provided by XOOPS Debugbar 1.3.0. This tool allows a developer to systematically carve away variables using live data, narrowing the search space down to the exact line of offending PHP code. True performance optimization requires diagnosing the structural reality of a live production environment, not the artificial simulation of local development. The first step in this deconstruction is establishing the time split. We carve the total request time into boot, app, and SQL segments. An app-dominant state indicates that request time is being burned inside PHP logic that is neither framework bootstrapping nor database querying. This diagnosis immediately rules out the database. The focus shifts entirely to PHP loops and execution logic. Alternatively, a request might be boot-dominant. Here, framework preloads and event listeners act as an invisible anchor on request speed. If the data identifies the request as boot-dominant, tuning SQL queries is a total waste of resources. Establishing this coarse-grained time split dictates the trajectory of the investigation, preventing optimization dead ends right at the start. Sometimes the time split reveals a paradox. The server processes a request in milliseconds, but the client still waits seconds for a usable page to appear. Traditional server-side timing cannot measure client-side rendering blocks or unoptimized document object model structures. To bridge this gap, Debugbar uses Real User Monitoring, or RUM. It collects field metrics via beacons exclusively from authenticated admin sessions. The core metric collected is largest contentful paint, or LCP. This tracks exactly how long the user stares at a blank screen before the main content renders. When LCP is catastrophically high, but PHP execution is fast, the telemetry proves the back-end architecture is fine. The bottleneck is almost always a render-blocking script. Server-side timing is an incomplete truth. Without client-side rendering metrics, you cannot measure the gap between the server's response and human perception. If the initial time split points to SQL as the dominant layer, the primary suspects are structural repetition and database flooding. This usually manifests as the N+1 query problem, where a single loop in the application spawns dozens of nearly identical individual database calls. Debugbar aggregates these repeated queries by fingerprinting them. It strips away literal values to group identical statement shapes together, exposing the repetition. Knowing that a page runs 62 identical queries is distinct from knowing which line of code actually triggered them. By dropping the generic database driver and logger frames from the stack, call site attribution pinpoints the exact module and line number that triggered the flood. Instead of manually searching through a massive codebase to find a missing join, you are handed a precise coordinate, like itemhandler.php line 255. High-resolution call site attribution transforms an abstract performance finding directly into an actionable code edit. To fix a slow query, developers use the database's explain action to view how the execution plan will actually run in production. But allowing raw client-submitted SQL directly into a live production database creates massive, catastrophic security injection vectors. Debugbar solves this through a fail-closed architecture. The browser never sends actual SQL strings to the server. Instead, the client only posts a request ID and a cryptographic statement hash. The server resolves this hash against a short-lived stash it recorded itself, guaranteeing authenticity. Because this stashed copy is redacted, with all string and numeric literals replaced, no session ID, password, or authorization token is ever persisted to disk or sent over the wire. Deep system telemetry is only viable in production if the diagnostic pipeline is engineered to be as secure as the application itself. Resolving a single slow request is useful, but the real value lies in analyzing the behavior of the entire application across a multi-day administrative window. Isolated profiling provides merely a snapshot. Aggregated analytics reveals systemic architectural realities. A prime example of this is the per-request block cache split metric. Tracking uncached versus cached block renders exposes heavy database queries that are being unnecessarily repeated for every single visitor. Identifying these systemic bottlenecks allows developers to remove more request time with a single caching fix than with days of micro-optimizing code. True high-impact optimization scales only when it is based on aggregated historical data, rather than momentary observation. This creates a deterministic workflow. You select a slow URL from the aggregated telemetry, reproduce it, and let the diagnostic pipeline carve away the variables. Applying the time split, tracking LCP metrics, and utilizing call site attribution removes guesswork from the development cycle. Teams can enforce strict performance budgets for boot time and query counts, catching regressions automatically before they impact users. Every code change can now be measured for exact impact across the entire stack. XOOPS Debugbar 1.3.0 transforms performance optimization into a deterministic science of measurement.